Thank you all for coming. Today we're going to talk about one of the hottest topics in Iceberg and in data, which is streaming. As you can probably see in the conference, Iceberg is becoming super, super popular. But streaming with Iceberg is still quite a challenge. How do you handle all of the challenges that come with streaming while keeping the benefits of Iceberg? So let's get right into it. So quickly about us, maybe it's for today. I'm Yuval, I'm the CTO at Ryft. This is Nitzan, he's an engineer at Ryft as well. 1 second.
It helps.
Oh, much better. Ryft is an Iceberg management company, so we handle with a lot of customers having a lot of streaming data into Iceberg. So first of all, how do you even stream to Iceberg? At the beginning, the only tool that supported this was Spark Streaming. Okay, that was back in 2019. And then quickly open source engines picked up. Flink, Trino, and Kafka are super, super popular today. And then coming into 2025, there's also a ton of vendors streaming into Iceberg, and you can also find them here today in the conference. Now let's see what's happening when you're streaming data into Iceberg. So every column here is a new snapshot created by a micro batch from the streaming. So let's say you're streaming every minute. So every minute, what's happening is that all of these files are getting created. So you're going to create a new metadata JSON file, a new manifest list file, a new manifest, and then the data files actually created for that minute specifically. And then another minute goes by, and you're inserting them again and again. You can see how many files are getting created here. And this is when you're only doing appends. If you're doing upserts, if you're merging data into your from your stream, then that's even worse, because sometimes you're even creating additional delete files, and that gets complicated where you have to start joining existing data with the data that you're streaming in. Right. So today we're going to cover the 3 biggest challenges with Iceberg and streaming: small files, active storage, and merges. And we're going to show you how to solve them as well. The first one is small files, and I'm sure everyone has already kind of heard the small files problems, even from the Hive days, right? So what is a small files problem? It's very easy to understand. We have tons of data files. We also have tons of manifest files created by this stream. We can get hundreds of thousands of those files accumulated in a day. For example, if you're streaming every minute or every few seconds. Now, why is that the problem? If I'm an engine and I want to query that data, the work I have to do, the back and forth I need to do to the S3, GCS, wherever your storage is creating a huge performance impact and API costs that are going to accumulate. Also, if you think about things like compression behaves much worse when the files are splitted, right? Statistics of the file, the min-max of the files are much, much wider than if everything is together. So this is really the situation we want to avoid. I think this is the biggest problem with streaming in Iceberg. Now, how do you solve that? Well, the answer that maybe everyone else is thinking about is compaction, right? Compaction is one of the most important things you have to do in Iceberg to keep your tables in check, especially in streaming. So what is compaction? Very easy to understand. We take a bunch of data files and we compact them together. So we had 5 data files and we compacted them into nice, bigger 2 data files. So simple enough, right? Probably solves the problem. However, it kind of gets a bit more complicated in streaming. Why is that? So let's compare 2 compaction strategies and see how they compare to each other. So on the left here, we have, let's say we are streaming every minute, and every minute is a new 1 megabyte file is being created. On the left, we wait after 10 minutes, and we compact all the data that was accumulated. So we compacted 10 megabytes, and we got the 10 megabyte file out. So seems simple enough. However, on the right, we're doing a much more aggressive compaction. Let's say we're compacting every 2 minutes. So you can see how we're not waiting for 10 minutes, we're compacting after 2 files, and then we're compacting again after 2 files, and again after 2 files. At the end of this result, we might end up with the same output files, so 1 file here and 1 file here, but if you count the number of data that we actually read and written, we get 44 megabytes here, so maybe almost 5x more work to be done in order to compact the same data. And this is just to show you how different strategies can actually really affect how much money does it cost you to compact. And the trade-off, of course, is what is the SLA of your most compacted data, right? Here, we waited 10 minutes, or this could be also an hour, right? So if you're querying those files before compaction, you're going to get the worst performance and API costs and et cetera, et cetera. However, here, you spend more money on compaction itself, but get a much lower SLA. So the way to think about it is basically on those two axes, right? How much does the compaction cost me? I can do it much, much more aggressively. And in the other axis is how many actually small files are being read, right? So maybe it means that different tables need different compaction strategies. If you have tables that you're only querying once every quarter to make a report, they don't need an aggressive strategy. However, if there is a streaming data that you're querying every minute, you probably want a much more aggressive strategy. So the main considerations are when to compact and what to compact. And there's a third thing, which is how to compact, and we won't cover here. In terms of when to compact, the things you can think about are, when not to compact, right? When can we avoid this operation at all for tables you're not reading, for data that is not so important, et cetera, et cetera. The other thing is that you can look at either the commit rate of the table, the number of files accumulated across the table, or just do it in an interval-based. In terms of what to compact, if you're working inside a budget and you don't have unlimited resources, you really want to prioritize. You can prioritize across tables or actually across partitions in specific tables. So let's say you're partitioning your table by day. It might be more important to compact recent partitions from the last week than to compact the data that you just backfilled from a year ago or something like that, or the other way around, depending on the business needs.
Thank you, Yuval. I'll take it from here. Again, I'm Nitzan. I work at Ryft as a software engineer. And let's talk about active storage. So active storage, we define it by the size of your current snapshot divided by the size of your total snapshots. This can be broadened into the size of your current snapshot divided by the size of your entire bucket or storage. Why is this important? So let's go through this example for a second. On your left, you can see two data files being written. You compact them, you get a bigger data file of 2 megabytes. Another file is being written, and then another compaction happens. You end up with a file of 4 megabytes. Out of these 9 megabytes that you're storing, you're actually using only the latest snapshot, which is only 4 megabytes. Out of 9 megabytes, that's about 44% of storage you're actually using. That means that there's 64%, 56% that is not being used and you're paying for. And a good thing to handle this is when you're compacting and you're streaming and you're being responsible, but you're still keeping track of the unused snapshots, is to retain what's called a snapshot retention strategy. So it depends on your use case. If you're streaming very often and you want to retain only the last week or so of snapshots, then you might consider defining a strategy that is about a week or so worth of snapshots. But if you're interested in just keeping an absolute number of snapshots, that's also possible. That depends on your use case. But the thing is, a good rule of thumb of active storage is to keep it above 85%. Make sure that you're not paying too much for unused storage. And also just making sure that you're using the right snapshot retention strategy depending on your use case and your read use cases. All right, so to sum up, until now, we talked about compaction, we talked about snapshot retention, and now I want to talk about merges. Merges is a very costly operation when we're talking about Iceberg specifically, because when you're streaming, you don't want to have this costly operation affecting your latency and your throughput. So let's imagine you have your source database on your left side, which is the S letter, and on the right side you have your target database, and you're mirroring, right? You have a CDC operation going on, you're mirroring your production database, and you're streaming it into Iceberg. A lot of costly operations can happen in this phase, right? You're joining, you're trying to understand which files to upsert, and then you want to overwrite these files. There are two main challenges in these phases, which can cause latency to go up, and throughput to go down. So let me first talk about the overwrite phase, which you might want to optimize. When we're writing, we can define what's called a write mode, or a write strategy, or a merge strategy. For the right side, it's called copy on write. It's a strategy that is the default for your table. which is when you copy the entire file and you rewrite it. That's very cost. It might affect your writing because you're actually rewriting the entire file. And if you want to stream and you want to write very fast, that might affect your throughput and cause it to go down. But it makes your reading very fast because your file is just ready to go. Your query comes in, it reads your updated file, but you pay the price when you're writing. And if you're writing very often, very large batches every minute, that might cause the writing latency to go up. On the left side, you might want to consider merge on read, which is a strategy that involves you not rewriting the file, but creating a delete file instead, which is a much smaller operation and a much cheaper price to pay when you're streaming. But you do pay the price when you're reading. So if you want to read very fast and very often, you might not want to consider a merge on read. Sorry. So it depends on your use case. If you want to read very often, you might want to use copy on write. But if you're streaming very often and you want to read every once or so, and also you can combine it with compaction, which takes these delete files and merges them into one clean file ready to read. So it's up to you on your use case. But often when streaming, you might want to consider merge on read because, again, you write much faster and you can pay the price when you're compacting and you're doing your maintenance jobs. Okay. Now we talked about the overwrite phase. Let's talk about the join phase. Joining is a very costly operation, and Spark has this hidden optimization, not very hidden, but it's hard to get to, which is called SPJ. It's let me look at the example on the left side. So you can see you have two executors going up, and the join operation is being initiated. And you have what's called a shuffle stage, is where each executor needs to understand which files to work on. And this is a very costly operation because executors need to talk to each other and understand which files to work on, which might take a lot of time and might affect your throughput, etc., etc. But when you're activating SPJ, which is what's happened when your target table and source table are aligned, you might skip this shuffle phase and get directly to the executor join phase. That saves the communication between each executor and keeps the work locally inside each executor. So make sure when you're joining and you're running your Spark operations that you have this optimization turned on. You can see it when you're running in the Spark operation and you can explain it, and you'll see that the shuffle phase is entirely gone. So that's a very important optimization to take into consideration. Okay. Something to take into account as well is what's called a commit conflict. So you started your join, and as you're doing your join and you want to upsert, suddenly this file is being rewritten under your feet. This causes the entire operation to abort, and you just wasted all of these resources for nothing. So I think the most foremost is to make sure you're tracking these commit conflicts. You're either writing it in a fail queue, or you're monitoring it, or you're measuring it, because again, these are very costly operations. And you need to be aware that your maintenance jobs aren't screwing up your compaction, your commits and your merges. Because if you have a large DBT operating, you might not want the compaction maintenance job running with it and causing commit conflicts. And yeah, as I said, just keep track of it and do it responsibly.
All right. So I think if you want to take something from this talk, I think it's these four. Firstly, Iceberg and streaming works wonderfully together. We see it all the time across customers around the world, streaming petabytes of data yearly. And it honestly works quite well. And comparing to all the alternatives, the cost efficiency is sometimes 50% or 100% even better. I would say that the three biggest challenges is what we described. And the first thing is to take a look at your compaction processes. First of all, make sure you're compacting and you're kind of airtight in that sense. So monitor your files, monitor your partitions, but also monitor the resources that the compaction jobs are taking. In streaming, it's very easy to get to a situation where you're kind of recompacting the same data over and over again, like we saw. So I would measure the number of files, measure the resources that you're putting into, and finding that trade-off that works for your organization. Next is the active storage, and this is something that's very easy to miss, just because when you're looking at the table looks perfectly fine, but actually it contains so much data behind the scenes on your object storage, and that just takes a lot of your storage and money, basically. It's very, very common for us to engage with a new customer and see active storage below 50%, meaning, for example, in a table that weighs 1 petabyte, that means 500 terabytes of S3 storage that is just really unused. So aiming for the 85% mark is kind of like a good rule of thumb. And again, the way to calculate it is just to look at the current snapshot, look at the entire snapshot tree, and just compare the two. It's actually pretty simple. And lastly, if you're doing merges, and I'm saying if because if you can resort to do append-onlys, that is much, much more recommended, but you can't do it all the time. If you're using merge, you have to look at two things. First, decide on your strategy. So copy and write versus merge and read. That's a huge decision you have to take. You can, of course, change it along your journey on the same table. There's no problem, but it's a very big decision to make, depending on the trade-off needed. And make sure that you're merging on the right partitions, on the right keys, and try to get to a situation where you can apply SPJ. Again, by having the target table and the source table share the same partitioning spec. So again, Iceberg and streaming works really well. Beware of those challenges. And that's it. We're happy to answer any questions if anyone has any.
Thank you.
Thank you all.